All right. So more antennas. Directional, Yagis and parabolics. Talk about circular polarization, how you do it with a couple Yagis. Loading coils and top loading, basically for mobile antennas. And feed point impedance, again, for mobile antennas, because typically a mobile antenna is going to be electrically short. A little bit about antenna Q. And there used to be a question about RF grounding that they removed. And I didn't remove the label. So we talked about gain. We specified in dBi or dBd. We talked about bandwidth, which is measuring the 3 dB points. We increase the bandwidth by increasing the diameter of the elements on an antenna. So we're changing the length to diameter ratio. So the smaller that ratio, the wider the bandwidth. Seems intuitively the opposite, but.
And you can't just make them bigger in diameter because that affects their length.
The electrical length?
Yeah.
Yes. Yeah. If you change the diameter, you got to adjust the length for the same frequency,
Right.
Resonant frequency. So how does the antenna gain stated in dBi compared to gain stated in dBd for the same antenna? See, those questions we had earlier were for generals. So this is the same question for extras. Huh? Oh, excuse me. Just the opposite. So it says everybody's supposed to know. I think it's even on the technician.
I just remember the 2 point was well, the D, they want a larger number.
Okay, front to back ratio we talked about. It's the major lobe relative to the back lobe or power in the opposite direction. You can have up to, for some Yagis, you can get up to 20 dB, but there's trade-offs. The higher the front to back ratio, you start sacrificing forward gain. So if you optimize it for the maximum forward gain, you get a lower front to back ratio. It's like everything, that's a trade-off. And then some other things you play with and you start getting more side lobes. So what does front to back ratio mean in reference to a Yagi? What's meant by the main lobe of a directive antenna? What if that's a typo? I would have thought it was directional. Delta. Oh. No, it's still there. Okay, so a Yagi consists of at least 2 elements, a driven element and either a reflector or a director. Typically, if it's a 2-element Yagi, you're going to have a driven element and a reflector because you get more gain from the reflector than you do from the director. The driven element is typically half wavelength long, although in most cases, for some reason, it's slightly smaller. And it has to do with phasing of all these different elements. The reflector is typically longer than the driven element. Directors tend to be smaller, and the farther away from the driven element, the shorter they get. So they increasingly get smaller. And the spacing changes. They get spaced farther and farther apart, depending on the distance from the driven element. With enough directors, you can get up close to 20 dBi. I think I've seen them with like 16, 18 elements, but it's diminishing returns. Every time you add another director, you get, maybe a half a dB or quarter of a dB. So at some point, it just doesn't pay to have it, that much longer, because each one of those additional ones increases the boom length a lot. And you got a mechanical issue of how do you support it? And usually you'll have the mast up above it, so you can have support wires down to the ends so it doesn't sag. They're very narrow bandwidth, only 2 to 3%, which if you use larger elements, you can increase the bandwidth. So they're usually made out of tubing with, half-inch diameter, stuff like that, depending on the antenna. What's the approximate length of the driven element of a Yagi antenna? How do the lengths of a 3-element Yagi reflector and director compare to that of the driven element? It's actually called a Yagi Uda. Yeah. Dr. Yagi and Dr. Uda. It turns out Uda worked for Yagi. Uda did most of the design. Yagi gets the credit. Just like it's the way the world works. If you increase the boom length and add directors, you can increase the forward gain of the antenna. If you use larger diameter tubing or elements, you can increase the bandwidth. If you play with the number of elements and their spacing, okay, and the total length of the boom, you can optimize forward gain versus front to back ratio and the side lobes. So there's all kinds of modeling you can do if you want to customize a Yagi for a specific purpose. Most of the time, if you build one, you're just going to look on the internet, find some formula that tells you what length to cut all the elements and what spacing, and go with that. What's the primary effect of increasing boom length and adding directors to a Yagi? Which of the following would increase the bandwidth of a Yagi? Which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi antenna?
Yeah.
We got a delta. One of the other things you can do is you can add more than one Yagi. If you space them one above the other, half a wavelength apart, you increase the gain by 3 dB, but you also have a narrower lobe in elevation. In other words, squishes the load. In free space, how does the gain of two 3-element horizontally polarized Yagi antennas spaced vertically a half wavelength apart typically compare to the gain of a single 3-element Yagi? What's an advantage of vertically stacking horizontally polarized Yagi antennas? Why do you normally do a Yagi horizontally? You get better propagation. And it's easier to do. Okay. Typically, they're somewhat less than 50 ohms. I think more like 35 or something like that. You can use what's called a gamma match, where the one advantage is the driven element can be one solid element, just like your directors and reflectors. And it can be connected to the boom. So you're going to connect one side of your feed line to the boom and driven element, and then the other side goes through this sort of capacitor inductor affair with a sliding rod that you have to adjust to get the right impedance. So there's a rod that's inside this tube, and that's the capacitor, and then you can change the inductance and the tap point by sliding the what they call the clamp in the picture. I've never tried to adjust one, but I guess it's kind of fun. The other way of doing it is with a beta match or a hairpin match, where you're actually using a transmission line stub or a piece of bent wire like they're showing there, which is why they call it a hairpin. And the spacing and the length of it, okay, has to be determined. That's one of the cases where you'd use the Smith chart to figure that out. But in order to do that, it has to be isolated from the boom, and the two elements are separated, just like for a normal way you'd feed a half-wave dipole. And you can use that same feed on a half-wave dipole. So which of the following is a characteristic of using a gamma match with a Yagi antenna? What is a beta or hairpin match? Okay. Like I mentioned before, on a Yagi, if you're adjusting the number of directors and the spacing to maximize forward gain, you decrease the front to back ratio. It's kind of, if you want a very directional antenna with a high forward to back ratio, you have to sacrifice gain and vice versa. So, you do the length of the driven element like you do for a half wave dipole, and you use the 234 feet divided by the frequency to get the length of it. It's actually 234 divided by the frequency and you get feet.
In the wrong place.
Yeah. This is just showing typical configuration. Now, in some cases, I've seen multiple reflectors where they might have maybe three, one above and one below. You get a bigger reflection. In some cases, maybe even a flat, like a reflector. Approximately how long is the Yagi's driven element? Let's see. Yeah, two element Yagi, normally you're going to have a reflector and the driven element because you get higher gain. I'm not sure what the effect is if you just have a director. Obviously it's going to be less gain, but I don't know what other.
Couldn't have just the reflector.
Huh?
You could not have just the reflector.
No. You can have a driven element and a reflector, or a driven element and a director. Okay. Like I said, I don't know what you get when you just have a single director. I've never tried to model it, and I haven't seen anything that shows it. And one of the reasons that you have a longer reflector and shorter directors is to control the phase shift of the reflections on all of these. So basically the way it works is the driven element radiates like a half-wave dipole, broadside. So part of that radiation hits the reflector and gets reflected back 180 degrees out of phase, except it's not quite because it's more than a half wavelength long. So that affects, if it was a half wavelength, it would be 180 degrees out of phase. So it comes back either more or less, I'm not sure which way. And at some point that adds to the signal being radiated by the driven element. And then you have all the directors, which are doing similar things. They're getting radiated and then re-radiating out at different phase shifts. So they're all computed. So all these things add up at some point in the far field. Why do most two-element Yagis with normal spacing have a reflector instead of a director? What's the purpose of making a Yagi's parasitic elements either longer or shorter than resonance? Okay, polarization. Normally you use horizontal to do DX or weak signal work on HF. FM operations like VHF, UHF typically does vertical. Whichever way you're going. Well, in the case of vertical, if you're doing point to point, you have to have a vertically polarized receiving and transmitting antenna. If they're cross polarized, you lose a lot of signal. If you're doing horizontal and you're propagating by refraction off the ionosphere, it doesn't matter because once it refracts, it becomes elliptically polarized. It's no longer linearly polarized. It's not vertical, it's not horizontal, it's an ellipse, which circular is a special case where the ellipse is equal in both directions. you can receive or transmit circular by making a cross-oriented Yagi, where you mount them on the same boom, slightly offset at right angles to one another. So, and then you have to feed them 90 degrees out of phase. And that way you get circular polarization because the pattern is rotating. So how can two linearly polarized Yagi antennas be used to produce circular polarization? Definitely got to get a new mouse. Yep. I know, it's getting worse too.
People start, they don't work with somebody that have a mouse pad.
Well, it doesn't seem to matter where I'm at. And even trying to put the cursor on something when you're editing and you can't get the cursor where you want. So if it got really bad, plug the old fashioned one. Let's see. Parabolic antennas, typically when you get up to UHF, a microwave, you get these dish or parabolic antennas. The larger the dish, the higher the gain for a particular frequency. Also, as you increase for a given dish size, if you increase the frequency, you get a 6 dB gain for every octave of frequency. So if you double the frequency, the gain goes up by 6 dB.
Same dish.
With the same size dish. So it's basically the surface area of the disk related to the wavelength that you're using. So the larger the dish is compared to the wavelength, the higher the gain.
There's 6 dB, 4 times the gain.
Mm-hmm. But you also narrow the bandwidth, like most trade-offs. How much does the gain of an ideal parabolic dish change when the operating frequency is doubled? Okay, an inverted V dipole, which is a half-wave dipole mounted such that the center point is higher than endpoints. And if those were approximately 45 degrees, then its feed point impedance is about 50 ohms. So you don't need a matching transformer or anything. Now, one downside is it's kind of low to the ground, so you don't get the optimum radiation pattern. Unless, of course, you were up at VHF or something. What's the common name of a dipole with a single central support?
Oh.
Log periodic. You used to see those typically on TV antennas where it's called a log periodic because the length of the elements and the spacing of the elements varies logarithmically. They don't have as much gain as the Yagi, but it's a wider bandwidth than a Yagi.
HF wants a heavyweight log period. They're gigantic. You know what I'm talking about.
Which of the following describes a log periodic antenna? Which of the following is an advantage of a log periodic antenna? Okay, INVIS, near vertical incidence skywave. So if we have a horizontal dipole that's down between a tenth and a quarter wavelength, we get a very high radiation angle of radiation. It's almost vertical. And that allows us to get extremely short hops. So if you had a typical, that same dipole that was half a wavelength high, you'd have a fairly low takeoff angle. So you're going to have a hop of maybe 1,000 miles or more. So if you want to talk to somebody in Tallahassee, it's not going to work. If you're relying strictly on, huh?
Why would we want to talk to anybody in Tallahassee?
I was thinking right there.
Jacksonville, Cocoa.
This guy's pretty mean.
Yeah. But like I said, it was basically kind of developed and promoted by the military for situations where there's obstructions and you need to talk short distances, which you can't do with normal propagation.
So you go up and long distance up and then long distance.
Yeah, there's definitely path loss, but
It makes the trip.
it's no more than the path loss you'd get for a normal refraction. So if I have a dipole near the ground, these are just showing how the pattern varies. Let's see. I don't know, but I guess this top one here, A, must be the cloud warmer.
One quarter or something down there in the corner.
Oh, A, okay. A is an eighth wavelength. B is a quarter. Yeah, quarter wavelength. C is a half. So your typical lobes for a half wave at optimum. D is 3/4 wavelength. So see, we got this big vertical lobe now. So our lower lobes are much smaller, got less power in them because we're sending a lot of power straight up. And then we go up higher to a wavelength. So we don't have this upper one, but we got these other higher lobes. So as you keep going up and up, you get more smaller lobes. So which of the following antenna types will be most effective as a near vertical incidence skywave antenna for short skip communications on 40 meters during the day? That was another thing. See, at 40 meters during the day, you're not going to get normal propagation. The beverage. Now, we had a guy that thought it was made out of Coke cans. Well, I think the guy's name was Beverage. It's a receiving antenna because once again, it's kind of like the rhombic. You know, you have a terminating resistor. And it's long. It's a wavelength or 2 wavelengths long. It's basically a strictly receiving antenna. It's high loss. Yes.
Why are they using 75 on coax instead of 50? Isn't that gonna be a mismatch to your transceiver? Or
Well,
receiver?
yes, but remember, it's only 1.5 to 1.
Put a transformer in there to give you a 50 on.
It's a good question.
That's what I asked.
I guess you'd have to ask the guy that drew this drawing.
Mr. Britton.
He's like,
But it also radiates along the length of the wire and receives along the length of the wire, because essentially you'd be receiving. So what's the primary use of a beverage antenna? Okay, multiband antennas. And we already talked about some of those, like the off-center fed and the in-fed, which is a multiband. You could have a fan dipole, which I believe the picture down there is a fan dipole. So it can receive and transmit on harmonics as well as the fundamental, which is how a lot of them work. You'll see them for 40, 20, 10, with 3 separate dipoles all tied together, basically. So which of the following is a disadvantage of multiband antennas?
So,
If you want to transmit on harmonics, it's good. If you don't want to receive harmonics, it's bad. You can have a multi-band vertical by putting traps in. So you essentially, depending on the frequency, in this diagram, they're showing it's essentially 3 different length antennas. So for high frequency, you're only getting the bottom part, A, for the 10 meters. There's a 12-meter trap for B, and then whatever the lower one is for that length, you get the whole length of the antenna. One of the downsides of traps is, like for 10 meters, your power is down here at the bottom being radiated. Ideally, you want the power up as high in the antenna as you can get it, or at least the middle. So what's the primary function of antenna traps? Okay, for an in-fed, we talked about, has very high feed point impedance. Most people that do POTA use in-feds because it's easy to toss it up in a tree or shoot it up in a tree. You just connect to the end of it. So what's the feed point impedance of an in-fed half-wave antenna? Magnetic loops. They've become popular. I think they're still expensive from what I've seen.
they are expensive.
I never have tried one, so I don't know how well they work, other than that one I brought, the little $40 thing. Picks up a lot of noise. But they're also fairly portable if it's a smaller loop. And they do have this kind of figure 8 radiation pattern. If you notice a little picture on the bottom right, there's a tuning capacitor at the top of the loop,
bottom left.
bottom right. Where's my thing here?
That's the left.
You're right. I was seeing a reflection in my glasses. And you have to have some way to vary that capacitor, and it has to be very high voltage. You're talking about like at the end of those elements, so you're, several thousand volts potentially. They're usually expensive capacitors, vacuum type. And that's one of the reasons these things are expensive. And then, of course, you don't want to be standing next to this thing with your hand there tweaking it. So you have to have a way to remotely adjust it, which is another reason why, because you get a little controller with it that remotes it and does the adjustment.
Motor driven or something?
Yeah,
Really?
yeah.
Yeah, that's why they're so expensive. They're complicated as hell and expensive as hell.
And you don't want to be that close to it.
Is it any good?
Oh, I understand. They work great.
Went for sale at the last Hamfest, but I think people have like $500 or something.
Well, that sounds about normal.
Yeah.
You go to HRO, they got some there and they're $500-600. Like a 3-foot loop.
There's no inductance changing, it's only the capacitance.
Because all the ones I've seen. Now you can build one at home out of PVC and make a sliding capacitor, but you still have to have some way to kind of remotely tune it.
Stick.
Huh?
They go along stick.
Yeah, or a rope.
Stick.
Oh,
Yeah, like the backbone.
yep. In which direction or directions does an electrically small loop less than a 10th wavelength in circumference have nulls in its radiation pattern?
No.
Broadside to the loop. So
Well-
the loop is apparently this way.
Oh, okay.
I like all that, because I'm so happy with the direction planning. But,
But see, the problem is it's got two nulls. So which one is this one or this one? That's why the card.
They're both broadside.
Yeah, no, but he was talking about direction finding
Oh,
because it's got two nulls.
then use two magnetic loops halfway length apart.
Yeah. Right.
90 degrees out of phase.
That takes two people. Where if you get a cardioid, it takes one person.
back in the days when they still had flight service stations, they had direction finding loops when Joe Blow, the pilot, got lost. That's how they would tell him what direction they go.
Yeah, I used to see those in old aircraft and they had the loop. You kind of wonder how they were able, which null did they use?
That was for the ADF. Yeah, back in the 30s.
Well, that's before my time.
Hmm?
That's before my time. A little bit.
My time.
Okay, the screwdriver. Everybody familiar with a screwdriver antenna?
Another expensive form.
Yeah, well, I don't think they're that bad, but I know some people that have had them. They say they work great. It's just a motor-driven inductor that can change the coil and raise and lower it in that thing, which basically changes the number of turns you have on the coil. If you're familiar with the Wolf River, okay, same kind of thing, except there you're manually doing it. This does it with a motor.
Put a motor on my Wolf River.
Yeah, there you go. But apparently they're very good for mobile operation for like HF stuff. You can mount it on the back and
So be careful about this.
so how does the screwdriver mobile antenna adjust its feed point impedance? A halo, because it looks like a halo, but it's a half-wave dipole, and they bend in a circle. And it has a I don't know, is that a gamma match? Not exactly.
Yeah.
Because it doesn't have an adjustment. But
Unless that piece slides one.
sort of a gamma. So it radiates in the plane of the halo, which is not what you would think. So, but I guess it is, because if you shredded it, if you uncurved it, you'd have a half-wave dipole, and that's the way it would radiate. So when you curve it, I guess the stuff in the middle cancels out, so you just get radiation around the outside of it. Oops. You didn't see that.
I think it's still Charlie though.
Okay. Antenna efficiency, mostly for mobile radios. Normally you're operating below their resonant frequency because they're short. And the radiation resistance that we talked about decreases, and the capacity of reactance increases the shorter it gets relative to the frequency. So if you remember, we talked efficiency, it was the radiation resistance divided by the total resistance. So if the radiation resistance is going down, the efficiency is going to go down. Most of the time, you've got some kind of loading coil on that mobile antenna to match it to 50 ohms. And it's essentially just canceling out the capacitive reactance. So you're adding inductance, which is why it's a coil at the bottom as opposed to something else. So they say it makes it look electrically longer, but all you're doing is canceling out the reactance. So you're going to make it resonant at that particular point. So how does radiation resistance of a base-fed whip antenna change below its resonant frequency? It decreased. 50-50
I see. Systems.
decreases the shorter it gets relative to the frequency, because it's becoming more and more capacitive. If it's longer than your operating frequency, it becomes inductive.
Does it become capacitive because it's less inductive? Or
Well,
or does
I guess-
capacitance actually increase?
well, if you remember a few weeks back, it showed those plots of frequency versus the length, and you get to the resonant point, your capacitive and then your inductive,
Yeah,
depending on whether it's series or parallel, because they're opposite.
ah, we have something from class there. Not much. Add provided there. No. Nice break in the class.
Okay,
Karen.
all right. Question?
No,
Okay. What's the function of a loading coil in an electrically short antenna? So why is there a coil at the bottom of a whip?
no.
Yeah. Okay, efficiency. Because it's a short antenna, and we just talked about the fact that it has reduced radiation resistance, because that decreases the shorter it is relative to the necessary length for that frequency. If I use a high Q loading coil, I can minimize some of the loss. So it would be a coil that has a high reactance relative to its internal resistance. Ideally, you would want to put your loading coil, since you're not using it as a trap, you're just trying to make it electrically longer, up in the center of the antenna. And that way you get some increase in radiation resistance, and you get a better pattern coming out of the antenna because it's higher. This chart over here is kind of showing the radiation efficiency versus that H2H1 ratio, which is where where the loading coil is located. So when H1 and H2 are equal, which isn't on the chart. Oh yeah, 1. Um, looks like it's probably H2 over H1. So it looks like H2 needs to be slightly larger than H1 to be at this peak. So it'll be up a little more than halfway according to that chart.
What's the line? The RG? What?
The
Cursor is.
Yeah, it's an RG.
RG is 0. What's RG?
I assume that is the resistance of the coil.
Zero.
Well, if it was 0, then you're obviously going to have a higher efficiency.
Zero.
It's a theoretical plot. So we're somewhere in between these two. So you're overthinking it. You're overthinking it.
Sorry.
Why should antenna loading coils have a high ratio of reactance to resistance? What's the most efficient location for a loading coil on an electrically short whip?
Oh.
I guess in the case of that plot where the theoretical zero resistance, it was slightly higher than halfway. But in the real world, if you had another series of intermediate plots, it probably came down to about 1. Let's see. Loading coil decreases the SWR bandwidth because of the Q. So higher Q gives you narrower bandwidth. So you have, you may have to tune your antenna tuner or your match as you go across a band because of the bandwidth, probably not as wide as the band you're trying to look at. What happens to SWR bandwidth when one or more loading coils are used to resonate an electrically short antenna? What happens as the Q of an antenna increases? Okay, top loading. I never totally understood this, where you add capacitance on the top and it improves the radiation efficiency. So if you've got a short antenna that's already capacitive, it never made sense to me that you put a capacitor on the top. But apparently they work. It's kind of showing some typical ones where you've got 2 or 3 little loops up there. Sometimes you can have a kind of like a wheel, or sometimes just spokes. And they all add capacitance at the top of the antenna. So what's an advantage of top loading an electrically short HF vertical antenna? Oh, and RF grounding, there's no question, but everybody knows. Well, there was a vice president of ARRL gave a speech at was it Hamvention last year? Seemed like not that long ago, about grounds, like you didn't necessarily need them. Just kind of didn't quite understand it. But anyway, you want a low impedance ground connection, which means typically flat wide copper strap. You can get by with braid indoors. It's not recommended outdoors because it doesn't hold up to the weather. Because of the skin effect, you need a lot of surface area because the RF current travels on the surface. So that's why braid works or wide copper strap works. And this is kind of showing a typical setup where a lot of times they'll mount I think that's what you may have right in the shack, copper pipe.
Some copper pipe bar or something.
Yeah. Typically they mount a piece of copper pipe and then tap everything into it and tie that to a external ground or grounds.
Goes to the same ground that the feed lines and the tower and all that kind of stuff.
Okay. Okay, so we talked about gain, dBi versus dBd, the 215, the front back ratio, what the main lobe is, Yagis, how the different elements spacing and length affect things. Stacking them gives you another 3 dB. I guess if you put 4 up, you get another 3 dB, right? Well, not if they're small Yankees. If you're doing it at, 70 centimeters, they're not.
Don't you lose something when you interconnect them? Lose a dB or so?
Theoretically, you get 3 dB increase. I don't know in practice.
No, I mean, when you get 3D because of the two antennas, but electrically connecting the two antennas.
Oh,
you get
yeah,
a
because
loss.
you got to have a phasing line. You got to feed it out of phase.
So that loss comes out of the 3 dB gain.
Yeah, but well, depends on how long it is. If you're talking VHF, UHF, you're talking about short cable. If you're talking 80 meters, yeah, you got a lot of cable.
280
Okay, we talked about gamma matches, beta matches, which is essentially a stub. Driven elements are half wavelength long, approximately. For some reason, they always, when you see these formulas, you work them out, they're usually less than half a wavelength. But I guess that's just compensating for velocity factor. So they're probably electrically a half a wavelength, physically shorter. Circular polarization, parabolic antennas, we get a 6 dB gain for every double of frequency. Invis, basically a tenth of a wavelength up to a quarter. You get a very high radiation pattern. Beverage antennas that are not Coca-Cola, and multiband, which has, because they rely on harmonics, they don't have very good harmonic rejection. Specialized antennas using traps to get multiband operation. You can do that on long wire or even in-fed. I've seen it with a trap in the middle. Magnetic loops, expensive. The null is broadside to the loop. And the screwdriver uses a motor to vary the inductance. And a halo gives you a nice omnidirectional plane, which I assume would be a fairly low takeoff angle, depending on the height of it. I don't know that I've ever actually seen one, but we'll get to a couple more I've never seen either here in the next section. We talked about efficiency, where it was as the radiation resistance decreases, the efficiency decreases because it's a short antenna. Where to put the loading coil. The higher the Q, the better the efficiency, but the lower the bandwidth. And top loading, you get some of the efficiency back.